This 7.1 is called reflection. There's a bunch of other stuff in there, but we will talk probably more about that tomorrow. All right, so this has a lot, it's very similar to waves because, as maybe some of you learned when I showed a couple of the videos, light behaves like wave, it behaves like a particle. It's a bit of both. Maybe sometimes it's neither. Everyone was trying to, 20, 30, 40 years ago, put it in either camp. Either it's a wave or it's a particle. They've kind of since abandoned that notion. It behaves a bit like both. Okay, so let's just call it what it is. It's its own entity. It's light. We're still confused about a lot of things, and hey, we may never know it, and maybe that's the point. Not everything's there to know and understand, unlike a lot of scientists think that's their job, but I don't know. Sometimes it's like sometimes these TV shows, X-Files rings a bell. When you finally find out it's the last episode and people years and years have been watching and they finally want to know the answer to this particular situation, and then the writer actually gives it to you, it's so disappointing. You know, it's just like, oh, why? Why didn't they just leave us hanging and just end the show? So sometimes the answer is not as good as the question. Light is a form of electromagnetic radiation. That's how we see. Okay? If you want to impress someone, that's what it is. That's what light is. It's a form of radiation. It travels, of course, at the speed of light, which is what? 3 times 10, good, some of us got it, to the 8, and meters a second is the units we care about. Mine's color, you guys aren't. But the part we can see is just that tiny little sliver right there. All of this stuff is the electromagnetic spectrum. Yeah, I did it. I don't know if it's good. Yeah. Okay, but all of this is the electromagnetic spectrum. Way down on this end is what we call radio waves. There's another picture on the next page I'll kind of highlight. But this is a nice graphic. This is actually a wave. There's one wavelength. Now this wavelength for some of these radio waves is huge. Kilometers long. Okay, and things in space actually naturally emit radio waves, like stars from a distance. That's how we can kind of see them. We can't see them with the naked eye. We can't even see them with a Hubble telescope, but we know they're there because we're receiving those waves in the form of a radio wave. Okay, so they actually program this telescope to register these waves, and then we see them. And see is an interesting word because you don't see them with the naked eye, but we know they're there. So using some kind of technology, because we know they're there and they register, we use the word see. Okay, even though it's definitely not in that part of the spectrum. Okay, long wavelength, low frequency. Is there an inverse relationship between those two? You bet. Remember this formula? No. Well, there it is again. I know you just had a test on this 2 weeks ago. If the velocity stays the same and I increase the frequency, the only way mathematically this thing's going to work is if that is decreased, right? So for example, if the frequency was 2 and the wavelength was 1, you know the speed in some unit is 2 times 1. Well, what happens if that's now 4 and I have the same speed? Then the wavelength must be, this has got to equal 2, right? It's got to be a half. That's an inverse relationship. So long or big wavelength, it has a low frequency given the same speed. On the other end of the scale, there's a gamma ray. Very, very powerful, high energy. That's what we use to kill stuff with. Hopefully the bad stuff, like cancer cells. Okay? You don't just spray it across the whole human being, because then they won't make it to see tomorrow. They'll be dead. So we want to concentrate that right on the bad stuff, the cancer cells. Kill those off. Hopefully the surrounding tissues are still okay, and you can go on functioning. Problem is, if it's in the brain, there's not much you can do, right? How do you irradiate part of your brain? It's just basically they give you 6 months to live and that's it. But at other places of the body, sure, you can pinpoint it. And they take it from a few different sources, zap that area, hopefully the rest of it's good, it doesn't spread, and maybe you're okay. High energy, okay? What happens with a wavelength? Very, very short or small. Very, very, this happens really, they're very, very small, let's say that. And a very, very high frequency because there's an inverse relationship here, okay? Radio waves, they're going right through your head right now. You feel them? How about all those cell waves, which are about this frequency right here? Cell signals? I mean, how many thousands of them are coming through here right now? Right? Sometimes they actually connect to your phone, given the right frequency. But they're all going through you right now. You don't feel them. You don't really know them. Okay? We're kind of adapted. It's all good. This stuff, you'll know if that goes through you. Okay? X-rays. You know when you go to the dentist, they give you a big lead cape to put on, right? Because you don't want that radiation going places where it shouldn't be. And you can only get an X-ray every so often, but once every 2 years. You don't want to do that more often because you're irradiating yourself. That's not a good thing. Because you want when you guys grow up and have kids, you want them to have the right number of limbs. Okay? So you don't want to do that too often. This they still call light, but you can't see it with your eyes. It's called infrared. We know that already. We've already seen it. Okay? It's a little bit lower in wavelength than the visible stuff, the stuff you can see. Okay? It's a little lower in energy, but that's what actually heats our planet from the sun. Just above it, they still call this light UV. You've seen that before? You know what that's all about? Should I tell you the story about when I was your age and I bought a cool looking pair of sunglasses that were like really cheap? $3. Do you think that blocked the UV light? Do you think I got a headache? My eyes turned red? I strained them? Here's the thing. It's even worse than not having sunglasses at all. Okay? Because what happens is your body thinks, okay, you're wearing these dark things, so I'll dilate your eyes to compensate for less light. So you're actually allowing more UV light to get into your eyes. It would be better off not even having sunglasses than buying ones that are cheap. You get what you pay for in life, right? So if you ever buy them, just to let you know, make sure they're 100%, and then they UVA and UVB, they categorize it, but make sure it blocks all of it, okay? You want to protect your eyes. Okay, so here's another chart. Same thing, long wavelength, low frequency, low energy. You kind of want to know the general, you don't have to memorize all this stuff, okay, but you got to want to know the general order of these things. It's worth a couple of marks. Above radio waves is microwaves. Radar, that's how we see things underneath ships in the ocean, okay, from space. We cook food with the same waves. Want to hear another little stupid story? I had in my last house a Panasonic microwave, operated at 2.7 gigahertz. Great, I could cook my food. Panasonic also makes a cordless phone. Same frequency, 2.7 gigahertz. Do you think if the microwave is on, I was able to talk to anybody? No. It's made by the same company, and they use the same frequency, so one interfered with the other. Is that ridiculous or what? Anyway. Okay. Infrared, that heats stuff, got to know it. Visible light, that's the stuff you can see. And thankfully, that's all we can see, because if you saw everything here, I don't know, you wouldn't even be able to walk. It would just be mass confusion. It would be like a huge, thick fog, probably. I don't know. UV, little higher energy than the stuff we can see. Higher energy, it damages your eyes. Make sense? X-rays, that would really damage your eyes. You don't want to do that. We know what we do with those. By the way, the guy who invented it, he X-rayed his wife so much she died of radiation. Wasn't very nice, was it? Highest energy stuff we know of so far, gamma rays. Okay? Really, really small. It's like the size of a nucleus. this comes naturally when things decay. I don't know how much time we'll get to do nuclear stuff, but we'll see. All right, high energy, short wavelength, high frequency. Everything I circled there, you need to be familiar with it. Okay, if you want the marks. Not so much. I mean, you don't need to know this versus that versus. This is all radio, right? Okay. All right, Roy G. Biv. Is that a little acronym you're familiar with from grade 8? Oh, good. It actually stuck.
That's the one.
3 years. That's the only thing you remember? Oh, good. Okay, so you don't have to memorize this, but it's about, 400 to 800 nanometers. That's the size of the wavelength of the stuff you can see. Okay? If white light goes through a prism, anyone seen the cover of Dark Side of the Moon? Sarah? Okay, you see that, what happens? It gets refracted into its different wavelengths. Because each one of these has a different frequency. They have a different speed, per se, all right? It gets refracted. And if you take that rainbow and put it back through the spectrum, then you get white light again. Wish I had the one to show you, but I don't. Okay, nano, what does that mean again? 10 to the minus 9. Micro is 6. Nano is 9. You don't have to memorize it, but some of you did accidentally, which is good. Okay. Infrared. What if we didn't have infrared? We'd all die. So it's a good thing. Ultraviolet. That's the stuff that burns you when you silly people lie out in the sun and get sun damage and decay. Block it. It's not good for you. You'll pay the price when you're my age. Okay, so something else you might have accidentally memorized in Science 8, light travels in straight lines. And then you get to Physics 11 and he says, no they don't. Most of the time we do. When we're doing our ray diagrams, we will assume that, but light can be bent. I think Einstein was the first guy who said that. He proposed it, and everyone went, either he's a genius, or B, he's nuts. And it took 20 to 30 years for someone to actually prove that he was in fact correct. It does do that. If you have a really, really strong gravity, the light will actually bend. How do we know that? Because we observe things out in distance and we know there's some star out here and there's another star behind it. And as this star moves, we see that that light looks like it came from a different spot. So it actually bent around that star. That's how they know about black holes too. Because there's an absence of light, and then all of a sudden as something moves, we see that light, and then it disappears again. So black holes actually suck it in. It's so massive that even light doesn't escape. You probably heard that. Okay, ray diagrams, that's more tomorrow and the next day. Okay, the law of reflection. This is also from Science 8. We have an incident ray. That's where it came from. Okay, it's incident upon the mirror. That's just some strange language that maybe you're not familiar with. Well, you need to be. We're doing it today. It gets reflected because it's a mirror. This is how you see yourself. That's how you see that light bulb there. Only it wasn't a flat mirror, it was a curved mirror. By the way, it flipped the light bulb, didn't it? If you looked at it in the tank, it was upside down, and it made it right side up, didn't it? Okay? Hits the mirror, gets reflected. This is called the normal again. That's just a fictitious 90-degree angle to the surface we're talking about. And the law says the incident angle is always equal to the reflected angle. Now, R is kind of confusing because we're going to be talking about refraction in about 5 minutes. But we kind of know this, right? This shouldn't be new. And if it is, well, know it. Okay? The angle of incidence is equal to the angle of reflection. Okay, flip on over to page 226. That was reflection. This is refraction. Yes? If you mean the picture looks like it's doing something weird, yeah, don't ignore these two lines. If that comes in at 45 degrees, it goes out at 45 degrees to the normal. Okay? Now let's talk about refraction. Is this a familiar word? I hope so, because we did it. But that was like, I don't know, 17 days ago, 18 days ago. And I showed you a pencil that went in a beaker of water, and what happened? In that case, it kind of maybe looked like that. Same thing happens with light. If that goes in, there's our normal. And because it goes in a denser medium, it bends towards the normal. That's refraction. It's a bending of the light ray. Because it's in something thicker, okay, it slows down and it refracts. This is also refraction, but lenses, I don't know how much we're going to talk about it, but this light ray comes in, it gets bent from the material, but also because of the edges. And some of you guys have done this with a magnifying glass. I've talked about it. You burn stuff, and it's kind of cool when you're in grade 3 and 4, right? That was like the best part of science up until physics. You still do it. Awesome. I showed you waves, and this was on your test. And they come in to something shallower. Maybe it's a ripple tank. Maybe it's out in the ocean, and they come into shore. It's not always, shore isn't always gradual, right? Sometimes you do actually have drop-offs. You have cliffs. And what happens is they actually slow down, let me exaggerate it, and they bend towards the normal, and the wavelength gets shorter, okay? Frequency stays the same, but they slow down. This is people. And yes, this actually happens as well. If these people walking from the pavement into mud, they would actually slow down, because you know you can't walk through mud as quick as you can on pavement, and the lines would actually refract. Same thing if you're driving on the road. Someone just got their license over the holidays. If you're hitting the shoulder, you ever see people that kind of said they got sucked into the ditch? Yeah. That's essentially what happens. Your wheel goes from something like pavement into something denser, like the shoulder, mud. There's other factors, but this is part of it. It actually slows down and it tugs on your wheel, and you actually end up going into the ditch. So now, of course, it does bend this way. The roads are actually crowned, so that's another factor, but this is partially why it happens as well. Snow, same thing. Okay, it slows down. It actually pulls you right into the ditch. You have to overcorrect. Sometimes that doesn't even help. You end up in there. Okay? Now, last thing. The first fellow who observed this was named Snell. So they actually named this law after him. There's a picture. I'm going to redraw it. That is an incident ray, because now we're not talking about waves, we're not talking about people, we're actually talking about one ray of light. Okay? Think of a laser. Yes, one little ray, one stream of photons. So some of those videos I showed you, you actually have to put slits there, because you know light, what's the word I'm looking for? We want it to expand and fill the whole space, so it bounces off everything, comes to our eyes, and then we can see better, right? That's why they cover those incandescent light bulbs. It's actually a filament, and we cover it with a special kind of glass to diffuse, there's a good word, diffuse the light. We don't want it to be as pinpointed. It's softer on the eye when you look at it too. So anyway, this is just one ray of light. There's our normal, which should be looking like it's 90 degrees to the surface. What is the surface here? Well, this is a boundary. That's not a mirror. That's a boundary between one medium and another medium, or two substances. In this case, it's air and water. Now, because these are different substances, they both have what we call indexes of refraction. So this one is Ni, or the book calls it N1. I'm going to stick with I, because that's the incident part, right? That's where the ray comes from. So we're calling that the incident medium. This is, as we know, it gets refracted because it's either denser or maybe some cases less dense. So we have some index of refraction for that material. This is the angle of incidence, and if this is denser, and we know water is denser than air, then if you memorize this from grade 8, wonderful, let me exaggerate it, it gets bent towards the normal, okay? So this angle is definitely less than this one. And we call that the angle of refraction. So we all, well, not we, but people knew that, but the first guy that came up with an actual formula that is observed to work, tried, tested, and true, his name was Snell. So we call it Snell's law. And if you're curious, that's where he was from, that's how long he lived. Not very long, which was typical of that area, right? Now the average life expectancy of a male is about 77, I think. Back then it was like 35, 40. Meryl? And index of refraction. Here, let's go on. So there's the formula. There's the wordage you're looking for right there. Okay? N is a constant for a given medium. They've tested, they've tried it, they've put it through studies, and they came out with this number just based on scientific evidence and data and conclusions. We know this is what happens. They've measured it. So now we got a little table we can actually use. I skipped over it, didn't I? Here it is. Okay, so you're going to refer to this thing when you're doing some of your questions. And I'm going to give you actually a worksheet from somewhere else that has some different indexes. But we start with a vacuum, space, and we say, okay, well, that's basically as undense as you can possibly get, as far as we know. So we're going to say that's 1. So as it goes through thicker substances, it bends more, so the index goes up. Air is not 1. It's 1.00029. It's pretty close to 1 though, so in your calculations, that's all you're going to put in. Okay? This is significant digits per se, but as far as calculations, they're insignificant. It's not going to change the angle much. Okay? As you can see, things get denser. Glass, it's pretty transparent, and that's good because that's what we use for our windows, right? So, but it does bend a little bit through there. It is a little denser than air, as you know, because it hurts more when it falls on you than a chunk of air. That's 1.5 to 1.9, depending. Is it green glass? Is it clear glass? Blue glass? You know. Okay. What's the hardest substance known to man?
Hardest natural.
Yeah. That's a trick question, isn't it? Yeah. It's not diamond, but let's just say it's diamond. 2.42. There's stuff that's harder. Okay. I'm not going to get into chemistry, but whatever. Quartz crystal, 1.54. Okay. So between 1 and about 2.5. That's what we're looking at for N's. That's your possibilities. That's an index of refraction. And again, that's based on observations. How much does it actually bend through there? You could do a whole course on diamonds. Why it's cut in a specific way, right, to make them sparkle. And you can see colors and things. Anyway. Okay, Snell's law. That's it. How many variables do we have in this formula? Destiny? Yep. There's 4 things in there, just like anything in science or math. You got to know 3 of them, or you can't do it. Okay? So every question, we might be asking for the index incident. We might be asking for the index, like what material that is, refracted, what angle did it go in at, or what angle did it come out at. That's it. That's all we can ask you. Okay, the rest is just algebra. So, light entering a block of glass at an angle of incidence, that is theta I. What else do I know? I know this glass, that's going to be, now you notice it says N1, N2. Yeah, I don't care what you use, but when I'm doing this question, I think it makes more sense to do this. This is the refracted one. So I'm going to go NR, not N2. This is the incident material. So I'm going to go N incident, not N1. You agree? Well, too bad if you don't. That's what I'm doing. Okay? This is N. It enters a block of glass. Well, from what? Let's keep reading. It leaves the boundary between the air and the glass at an angle of 12 degrees. So, I strongly recommend you do pictures for these. This thing comes in. What does it enter? It enters glass. From what? Where did it come from? It came from air. This thing's going to bend towards the normal. Okay? What is the index of refraction? That's what we're asking. So I better know the other 3 things. Do I know the index for air? You bet. It's in my table. You're just going to use 1. Okay? So, N incident equals 1. What else do I know? The angle of incidence is 18.5. So the only thing I don't know is that guy. So it's your choice. You can rearrange this formula for this guy. How do I solve this thing for N2 or NR? Divide that away. Or what some of you guys will do is put in the numbers first. Okay? Doesn't matter. Your choice. So NR is NI times sine theta I. This is just the formula. I'm not putting anything in yet. Over sine theta R. Which I do know is 12 degrees. Okay? Now put in the stuff. Ni is 1. Sine of theta, theta is 18.5, so I got sine of 18.5. And on the bottom, I just have sine of the angle of refraction, which is 12 degrees, so that's sine of 12 degrees. Pull out your calculator, make sure it's in degrees. And then put it in. You got to use brackets there, right? On the top one. Does it look like something that makes sense? N should always be between what and what? 1 and about 2.5. It can go higher, but in your questions it won't. Okay, does it look reasonable? NR is 1.52. This was glass. Let's look at our table. Look reasonable? You bet. Okay, always look at your answer. Does it make sense? If you got like 10.8, nope. Okay? One more. Light is incident on a diamond, girl's best friend, at an angle of 10 degrees. What is that? That's the angle of incidence. What angle will it refract? Well, so far it looks like I only have one piece of information. You got to have three. What are the other things? Yeah. I know N, it's incident on a diamond. It comes from where, we're assuming? Yeah, it doesn't say the person's swimming, so it's in the water, right? So N incident is 1. What is N refracted? It's on your table. 2.42. They don't give you a whole lot of room like usual. Okay, here's your formula. Okay, and on the back of your book, of course, it looks like that. You can't write it any other way. It's all you get. What are you solving for? I'm solving for sine theta r. So remember, I want the angle. I don't want sine theta r. When I'm all done with my calculation, I got to go inverse sine, right? So divide both sides by nr. So sine theta r is ni sine theta I over nr. Ni is 1, because I got my picture right here. Theta I is 10 degrees over nr is 2.42. So sine of 10 bracket divided by 2.42 is that. Does that look like an angle? No. What do I got to do, Reese? Inverse sine of the answer. Some of you guys still don't know this helpful button here, right? Inverse sine of the answer, don't have to plug it all in again and write it down, is 4.1 degrees. Does it look reasonable? It's going in a denser medium. It's going to bend towards the normal, so it's got to be something less than 10. Remember, this is the densest stuff that we know of so far, in your book at least. So does 4 degrees look reasonable? Yeah, sure it does. So 4.1 or just 4, I don't really care. Both ways, I know you're able to use this formula and get answers, so I'm okay. Okay, don't worry so much about sig figs here. I know there's 3 in this one. Don't worry about it. Okay? That's it. We got to fix one of the questions in your book first, but let me write down these. So 1 to 5 on the electromagnetic spectrum. Worksheet I'm going to give you just 1 to 4, and then come back and do this guy. Just watch the wording in this question. Think about what they're asking. Draw a picture. Might be a little tricky. I don't know. Okay, everybody got that? We got to fix a question first. Number 4. (210). We don't want frequencies shorter. We want frequencies higher, I believe. Yes. Okay, on page 210, number 4, fix